The single responsibility principle states that a class should have only one reason to change, meaning it should have a single responsibility or purpose. In other words, a class should do only one thing and do it very well. This does not imply that a class should have only one method or behavior, but rather that it should contain a cohesive set of behaviors related to a single responsibility. Let's take a look at this example. Does the book class adheres to the SRP? Let's break it down its responsibilities. First, it is representing data with properties like title and author. Second, it is managing the book data with the help of savebook method. Third, it is printing the book details with the help of the print method. Book class is handling multiple responsibilities and clearly violating the single responsibility principle. Let's see what are the problem if we do not follow the SRP. The code is harder to maintain. Changes to one responsibility might break others, making the code harder to maintain. For example, this class is used in 10 different places. One is using it for printing purpose, another one is using it for managing books, another one is using it for reading the book data, or it might be used in the UI as a model class. If you make a change in print method and introduce a bug, all the classes which are using the book class will break too. Understanding challenges. New developers might struggle to understand a class with multiple responsibilities, or this class might be too big and have a lot of code that makes it harder to understand for newer developers. Another problem is poor testability. Testing becomes more difficult as tests need to cover multiple responsibilities. Okay, let's redesign this class to make it SRP compliant. We can separate the responsibilities into different classes. By separating these responsibilities, each class now has single reason to change. The book class will change if the structure of book detail changes. The book printer class will change if printing logic changes. The book repository class will change if saving logic changes. This makes the code more maintainable, testable, and adheres to the single responsibility principle. The open-closed principle states that a class should be open for extension but closed for modification. In other words, you should be able to add new functionality without changing the existing code. Once you have written your class, it should not be modified in the future, except for the bug fixes. However, this doesn't mean you cannot modify your class during early development stages. It means that once your application or software is in the production and you want to introduce the new functionality, you should extend that class rather than modifying it, because you do not want to mess with code that is tested and working 100% fine. Now, a question comes in your mind: how do I add new functionality if I cannot modify the class? The answer is create a new class by inheriting the existing class and introduce the new functionality there. It is called extending the functionality. One can also achieve it with composition and delegation. It is not necessary to use inheritance for that. The main thing is you do not have to modify the existing functionality. Let's take a look at this example. We have three classes here: circle, rectangle, and square. We have an enum shape type containing the entries for each classes. We have class shape which have a draw method. Draw method draw the circle based on the shape type. Now let's draw a shape. For that, we need to create the instance of shape class, call the draw method, and pass the shape type circle to it. In the same way, we can draw other shapes. We just need to call a draw method and pass the shape type we want to draw. You might be thinking, that's okay, but what do you want to prove here? Let's say we want to introduce a new shape called triangle. For that, you need to create a class triangle, create an entry in the shape type enum, and you have to add one more switch case which draws the triangle. That seems totally fine, but what if in the future you need to draw more shapes? For that you always have to modify the draw method. The shape class is always being modified, and that totally violates the open closed principle. Our class should be closed for modification, but our class is open for modification. Let's redesign our application. Let's create the eye shape interface with draw method. Create the classes circle, rectangle, squares, which implements the eye shape interface. Each classes have its own draw method. Create a new class shape test which have draw shape method. It takes eye shape as an argument, which means we can pass any instance which implement the eye shape interface to it. Call this method and pass the instance of circle to draw a circle. For drawing a shape, we just need to call draw shape method and pass the instance which implements the eye shape interface. To introduce a new shape in our system, we just need to create a new class and implement the eye shape interface. For example, we want to introduce triangle shape in our system. For that, we just need to create a new class triangle and implement eye shape interface there. Now in the main method, we need to call draw shape method and pass the triangles instance as an argument. We can add any number of shapes in our system without modifying any existing class. We have many solutions to achieve the open close principle, but we are not going for that. In my opinion, this principle does not imply that we should never modify the existing code. That is totally impossible. But we should try to design our classes in such a way that it can be extended in an easy manner. I will put down the link of my blog post where you can find all the code used in this video. The Liskov substitution principle states that a derived type should be completely replaceable for its base type. In simpler terms, a child class should do at least what the parent class can do. The child class can have additional behaviors, but it must have all the behaviors that the parent class has. For instance, an animal has behaviors, eat, sleep, and make sound. A dog, which is a subtype of animal, must have all the behaviors, and those are eat, sleep, and make sound, which means dog can eat, sleep, and make sound. In simpler terms, if you ask for an animal which can eat, sleep, and make sound, then you must be okay with having a dog, a cat, or a horse. So that is basically the LSP. LSP is all about having well-designed polymorphic classes. Let's understand what constitutes bad polymorphic design. Bird is an abstract class that has methods like eat, make sound, sleep, and fly. Sparrow and penguin inherits from the bird class. Since a sparrow is a sparrow must do what a bird can do, such as eat, make sound, sleep, and fly, and it does. A penguin is a bird too, so a penguin must do what a bird can do, such as eat, make sound, sleep, and fly. However, a penguin cannot fly. When you call the fly method of penguin class, it throws the error. Therefore, a penguin is not completely replaceable for bird. This code violates the Liskov substitution principle. So let's refactor our previous example. Let's create the iBird interface. We need to have another interface which will have the bird's behavior with flying capabilities. Since sparrow can fly, so it will implement the iFlyable bird interface. Penguins do not fly, so they will implement the iBird interface. A subclass should extend but not contradict the behavior of its superclass. This principle ensures that any client code expecting an instance of the superclass can also work seamlessly with instances of any subclasses. The interface segregation principle is especially aimed at interface design. It states that clients should not be forced to depend on interfaces they do not use. In simpler terms, this principle suggests that an interface should not include methods that implementing classes don't need. It encourages us to create smaller interfaces over the big fat interface. Let's take a look at this example. Imagine you have an interface for workers in a company. We have an interface iWorker with methods work, sleep and eat. Human worker and robot class implements this interface. So both classes have to implement all of these methods. In the case of human worker, it is fine because human work, sleep and eat. But in the case of robot, iWorker interface forces the robot class to implement methods eat and sleep, but robot does not need to have these functionalities because robot does not eat and sleep. It is violating the interface segregation principle because robot is forced to use eat and sleep methods. Now, let's refactor this design to adhere to the interface segregation principle. In the refactored example, we have split the iWorker interface into three smaller interfaces: iWorkable, iFeedable, and iSleepable. Each class is free to choose the interface it needs. Now, the robot class have to implement iWorkable interface only, while the human worker class implement all three interfaces. By splitting interfaces into more specific ones, we adhere to the interface segregation principle, making the code more modular, easier to maintain, and less prone to errors. The dependency inversion principle states that high-level modules should not depend on the low-level modules. Both should depend on abstractions. Abstractions should not depend on details. Details should depend on abstractions. Let's take a look at this example. We have a class user repository with method getUserById, and we have another class user service which have a direct instance of user repository. GetUser method is using the instance of user repository to fetch users by ID. There are few problems with this code. One is the user service is tightly coupled with the user repository. And another problem is if you want to use different implementation of user repository, you cannot easily do it. For instance, you want to swap your user repository to user repository with different database. So here our high level module, which is iUser service, is depending on the low level module, which is user repository. Let's refactor this example. We have introduced an interface iUser repository with method getUserById. User repository implements the iUser interface. Now user service is depend on the iUser repository. User service class is depend on abstraction, not on concretion, which make user service and user repository loosely coupled. User service is not responsible for instantiating the user repository. If you have another repository, example user repository with different database which implements the iUser repository, you can pass its instance instead of user repository. You can easily swap user repository with another repository, but the condition is it should implement the iUser repository. User service don't care if you pass the instance of user repository or user repository with different database because both implements the same interface. You might be wondering what is inversion. What are we inverting here? First, we need to understand the traditional approach. Traditionally, high-level modules depends on the low-level modules. If we consider our first example, our dependency injection is like user service is depending on the user repository. Our high-level module is depending on the low-level module. But using the DIP, user service depend on the iUser repository, which means we are depending on the abstractions. A high-level module is depending on the abstraction and low-level module is also depending on the abstractions. So both module is not directly interconnected. That's it for now. See you next time.